Good evening, everyone. Am I audible to you? Can you please let me know if I am audible? Can you hear me? Okay. So, good evening, everyone. My name is Shafali Agarwal, and I'm a research scholar at IIT Madras. And today is our third TA session on the topic of basic construction material. So, in this week, mainly you might have studied about the different nature of materials. So, if we see the outline of week 3, in this thing you might have studied about the atomic structure and what are the different kind of bondings, which we have already studied in a school. Just a little overview of that thing, what are the different type of bonds which are present. And then coming up to the metallic materials, what is the lattice structure, what are the different defects in our material, and how grain boundaries affect the material properties, and what are the different phase diagrams. So this is what you might have studied in week 3. We will just go through all these topics a little bit, and then we will see the some question and answer session for this week. So first thing is like, what is the atom? So we all know atom consists of electrons, protons, and neutrons. So if we see protons and neutrons combine and form a nucleus, and along that our electrons move around in a shell. Uh, in a different shells. So if we define our electrons, they with electrons come the valency. So if we see here, what is the different electronic configuration and the valency of our any atom or any material. So if we say such as sodium, we will first check the atomic number of that material. Based on that, we will form the configuration of it. So sodium atomic number is 11, right? So 1 is 2, 2 is 2, 2p6. So how much it is? 1 is to 2, 2 is to 2, 4, 2p6, 10, and then 3 is 1. So it will be 1 is 2, 2 is 2, 2p6, and 3 is 1. So this will give us the electronic configuration of our sodium. So in this case, you can see the outer shell. The outer shell of 3s is not fully covered. So in SL, normally we have 2 electrons, but in this case we have only 1 electron. So our shell is not completed. That's why whenever we are writing sodium, we are writing it as Na, one positive. That means it can gain one more electron. So that is the valency of our sodium atom is 1. So I hope you understand what is the electronic configuration, how we get the electronic configuration, and from that how we can calculate the valency of our any atom or any material. So why all these things are important is the atomic structures and the bonding are very important in terms of metallic behavior. So one example you might have studied about the diamond and lead. So both the materials are just a carbon chain. We will say they are made of the different carbon bonds. However, the type of structure they have, if we say this a diamond have a cubic structure, whereas this lead have a hexagonal structure. So based on the type of structure, our material is changing. So if this is crystalline fully, and so we are telling that diamond is the strongest material. However, lead is very brittle in nature because its bonding is different. However, both are made from the carbon atoms. Their type of bonding will affect the material properties. So it is fully made of covalent bonds. So we will see different type of bonds, then we'll again come back to this thing. So next thing is how interatomic forces and distances will shape up the different properties of a material. So in this diagram, which is actually called as Condon-Morse diagram, this is distance versus energy. So if two atoms are there, they are at, when they are far away from the sorry, when the distance between two atoms is very high, there is no force of attraction between them. So slowly they are coming closer, and at one point, at a optimal distance, you will see that the optimal distance, the energy is the minimum energy. So at that point we are telling that is an optimal energy or a optimal distance for two atoms. And then when they are coming very closer to each other, then they will face a repulsion among them. Okay, so if we see, this is the journal Condon-Morse diagram. We are telling that when it is at a distance, two atoms are at a distance, there is very less attractive force. Then come a point where there is an optimal point, optimal energy, and then the force of sorry, and then what you say, repulsion will start. So, based on our Condon-Morse diagram, we can actually tell about the material properties. So, if this energy level, if we have a very high energy level, then we are telling that our bonds, the interatomic bond is very strong. So, we have a strongly bonded solids. However, when this well is very low, that lattice energy is very low as compared to the this one, then we are telling it is a weakly bonded solids. So based on our Condon-Morse diagram, we are actually judging the type of bond we have. So if our well is very deep, then we are telling it is a strongly bonded, and if its well is very low, then we are telling it is a weakly bonded solid. Same way for the temperature, we can tell how if sorry, in temperature, we are telling at different temperature at T0, T1, T2, our curve will keep on changing. This curve, if this is our hypothetical curve, it will change based on our temperature. So this is what we are telling thermal coefficient of thermal expansion. So based on that, our value will change, and we can say that uh, our well and the depth of sorry, this width and this depth will define the value of our coefficient of thermal expansion. So if we are telling this distance, that is delta r, so this will actually define the value of our coefficient of thermal expansion alpha. Okay, other thing is this was the energy versus interatomic distance graph. So when energy versus distance graph is converted to force versus distance graph, how we can see, so if this is the energy versus distance graph, it will change into this is the optimal graph of force versus distance. Okay, so if we see, attractive forces are increasing as we coming closer, and repulsive forces are increasing in the positive direction. So the average of these things will give us the force versus force versus distance graph. So this thing you can understand based on the uh, derivative. So force is actually is equal to the derivative of energy versus distance. So when you will derivate this graph or this equation, you will actually get this kind of graph. So at the point of minimum energy, our value of force will be 0. Okay. So at this maximum, du upon dr will be equal to 0, right? So from this thing we can calculate the force versus distance graph. Also, now what different points indicates in this case, just a minute. So what different points will indicate in this case is elastic modulus. So how you can calculate the elastic modulus, any idea? So the slope of force versus distance graph will give us the elastic modulus value. Okay, so more the steeper value, the more will be our elastic modulus. So df upon dr will give us the elastic modulus value. Same way tensile strength. When atoms are very far away, the material ruptures and the tensile strength will be reaching. So other thing is compressive strength. So in case materials are very closer to each other, we can calculate the compressive stress from the value of this force versus distance graph. Okay. So from this simple Condon-Moose diagram, you can get the many different properties of our system. Mainly what we are telling, elastic modulus. The slope will give us the elastic modulus, and what type of bond it is. The more the deeper well, more is the stronger bond. Less deeper well, less is the bond, and then the width will give us the thermal coefficient of thermal expansion. So this is what we have in the Condon-Moose diagram. Other thing is what are the different interatomic bonds you might have studied in this week. So we have two type of different force bonds. First is strong bonds and second is weak bonds. So strong bonds are also called as primary bonding and weak bonds are called as secondary bonding. So first thing is ionic bonding. So ionic bonding means transfer of electrons. So if we say sodium chloride, sodium have one positive, it can give one electron, and chloride have one negative, it can gain one electron, and these two react with each other. So this electron is being given to the chloride, so it will become this is called as ionic bond. That means transfer of electrons between two dissimilar atoms. Second thing is covalent bond. Covalent bond means sharing of electrons. Here we are transferring electrons, here we are sharing electrons between two similar metals. So both chloride atoms can gain one electron. So when they share these electron, so the valence electron cloud is full, and that point we are telling it is a covalent bond. It means they are sharing electrons between similar atoms. Also there are chances that there is a sharing of atoms between two dissimilar atoms. That is also called as covalent bond only. One of the special type of covalent bond is metallic bond. In metallic bond, what is happening, there is a mass sharing of electron among the several electrons taking place. So sorry. So So we have different metal atoms and there are electrons associated with them. When all these metal atoms come together, all these electrons form a sea of delocalized electron. There is a sharing of these electrons among all the metals, and that is called as metallic bond. So normally what we are calling it as, instead of sharing of electron, we are calling it as mass sharing of electron. So because multiple atoms are sharing their electrons, we are calling it as mass sharing of electrons among several atoms. Next thing is secondary bonding. So we have two type of secondary bonds, van der Waals forces and hydrogen bonding. So van der Waals bonds is the weak bond between two covalent bonded materials. So HCl, it is a strong covalent bond, and again there is the HCl. However, this chloride and this hydrogen of these HCl have a weak bond in between them, that is called as the van der Waals bond. So it is normally the dipole moment. So because of the charge among these atoms, there is a weak attractive bond, weak attractive force between these two atoms, which is called as the van der Waals forces. Last is the hydrogen bonds. So hydrogen means when there is a bond between a hydrogen of one atom, oh sorry, one molecule and any other atom of the other molecules. So that is called as hydrogen bonding. Normally, if we say water molecules among each other will have a hydrogen bonding of HH, right? H and O. They are the attractive forces between positively charged hydrogen and negatively charged any different atom. So in case of water, it is positively charged hydrogen and negatively charged oxygen. So that is called as hydrogen bonding. So if we see all this type of bonding, other than these bonding, what is the effect of these bonding on different properties of materials? Like if we see hydrogen bonding, we are telling about the water, about the ice, why ice is more what we say lighter in weight than water, how it is floating on the water. Then if we talk about the van der Waals forces, we talk about the different properties of material like surface tension, viscosity. All these properties are due to the van der Waals forces between materials. And then if we talk about the covalent bonding, how materials are very strong, like the example we have seen. We'll go back to that example. Okay, if we see these two examples, diamond is formed of the covalent bond between carbon atoms. That's why we are calling it as a very strong material. However, when it comes to lead, it is formed with the carbon atoms only, and they are interconnected through covalent bonded. However, one layer of this carbon chain is connected to the another layer by weak bond, mainly van der Waals bonding. Be- because of that, we can say that lead is not as strong as the diamond. So the type of bonding will affect the properties of any material irrespective of the type of atoms being used there. Okay. So next thing is the what we'll call as what are the different lattice defects. So see if we see here, this is a normal lattice parameters. Sorry, lattice parameters of our any material. So it has, this is completely called as space lattice, and one cell which is repeating itself to form a complete lattice is called as the unit cell. So unit cell is the smallest cell, what we'll say smallest cell which repeat itself to form a complete space lattice. Okay. So next coming about is the what are the different type of defects in a, what are the different type of defects in our material. So first type of defect is the point defect. Point defect means when there is a there are two type of point defect: interstitial and substitutional. So if we see this one lattice going on fully, and sorry, there are small materials or atoms which occupy the space between these materials, that is called as interstitial point defect. However, when one of these atoms is displaced by the another atom of another material, then it is called as the substitutional point defect. So one example of these type of, any example you guys remember about these type of defect? So if we see if we are adding sugar in water, so what is happening, sugar is taking sugar molecules are taking space in the spaces provided between the water molecules, that is an interstitial type of defect. Okay. However, when we are telling if we take example of NaCl, so what is happening? Sodium is replacing the place of chlorides and forming a substitutional type of point defect. So some examples when it comes to the civil engineering problem, some examples are solid solution strengthening, swelling of clay. So in clay also water will take up the spaces, empty spaces, and because of that clay will swell up. So if you I don't have that figure here. So if we see about the clay thing, clay is made of different layer of alumina and silica. So there is a gap between different layers. In that gap, when water fill up, the clay will swell up. So that is a type of interstitial point defect. Next thing is the line defect. So line defect is means when there are imperfection in the complete crystal lattice. So among a complete, if we say a line of, here what we are telling, one atom is replacing the another atom, or one atom is taking getting inside the complete lattice. In line defect, we are telling when there is a complete line of atoms which are mismatched or are getting displaced from their position, in the complete lattice. So if we see in this figure, we have two type of dislocation, mainly edge dislocation and screw dislocation. So when if we say this line, because of this line have a mismatched atoms, because of that there is a dislocation in this complete material, so that is a edge dislocation. However, when there is a torque, in this case if there is a torque, so if we see any paper view, sorry, a Rubik cube, you will move it, at that point, at that line where you are moving it, that is the called as the screw dislocation. Okay. So what is happening because of this? Normally there is a plastic deformation along this slip plane. So we are calling this plane as the slip plane. There will be a deformation at this plane because of this type of line effect. So if we come to the material thing, we have two type of problems. Material properties, how it is affecting the material properties. First is the ductility of material in metals. Second thing is the strain hardening or work hardening. Third thing is the surface defects. So surface defects, if we see, surface defects are usually when there is a problem in a complete surface. Mainly if we see from the material perspective, if there is a problem in a grain boundary or among the grain boundary or transfers to the grain boundary, that is called as the surface defect. So if we see here, we it is made of when material is any material is heated and cooled down suddenly, they will align themselves in one direction and in different direction, and there will be a type of grain boundary formed along it. So when there is a problem along this grain boundary, then we are telling it is a surface defect. So imagine if a defect is starting from here, so it will line up from this point, then this point, it will go along the complete grain boundary because it is a weakest point, right? So that will be a type of surface defect. So one example of this thing is grain size strengthening. And last thing is volume defect. So volume defect means when there is a defect in the complete volume of our material. So normally when there are holes in our material, if we see, sorry, if there are different voids in our material, like in this example, if there are some voids in our material and that voids are filled with the foreign material, then they are called as the volume defects. Or if there is any what we say, what how we can like differentiate this type of defect from the point defect is, the point defect is usually in the two directions, and volume defect is in the three direction. So if there is a defect, any hole or any space in void in between a material in a three-dimensional area, then that is called as the volume defect. Okay. So if we see the example of volume defect from the material perspective, then it is like if there is a stress concentration and crack initiation and or precipitation hardening. So next thing and last thing you might have studied in this week is about the phase diagram. So phase diagram means how you are how, like in this case, pressure versus temperature of water. If we are increasing the pressure, and at lower temperature if we are increasing the pressure, our gas will convert into solid. However, at a constant pressure, if we are increasing the temperature, so solid will if any constant pressure, if we say like this, if I increasing the temperature, solid will convert to liquid, liquid will convert into gas, and that is called as the, this change in different phases of a material is called as the phase diagram. So this point, this line, where the solid is changing to liquid or solid is changing to gas or gas to liquid, these points are the different type of points we are calling as the. So if a liquid is changing into solid, a point where liquid is converting to solid is called a liquidus point, and solid is converting to liquid is called as a solidus point. Same way we have many other points which I don't know if you guys have studied about those points. Some eutectic point where two liquids are converting to one solid, that is called as eutectic point. So I'm not sure if you guys have studied all those things about the phase diagram. So mainly till this week you have studied about the binary phase diagrams and how the microstructure of our material will change depending on the different phases. So if a material is completely liquid, it will look like this. If it is completely solid, it will look like this. But however, in between somewhere where it is transforming from liquid to solid, at that point it will have liquid and some part of solid in it. So that is what is called as the phase diagrams. And this is a binary phase diagram where nickel percentage is increasing in copper. So we have 100% of copper. In that we are adding nickel percentage 20%, 40%, 80% to 100%, and how the phases will be changing according to the temperature. So this is what you might have studied in this week. If you have any question, you can ask me now. Okay, so I'm assuming that whatever has been taught to you in this week is clear to you. So we will see different few questions for this week. So first question is, which among the following is the correct order of the strength of bonds in journal? So is covalent bond is stronger than hydrogen, or hydrogen stronger than covalent, or hydrogen stronger than covalent stronger than ionic? Anyone who want to guess the answer? A. Okay. Correct answer. So we have seen that covalent and ionic are the type of strong bonds, and hydrogen and van der Waal are type of weak bonds. So if we talk about the strength of bonds, we would say covalent is much stronger than the hydrogen bonding. Second question is, materials will not fail in pure compression because of the repulsive and other forces when the atoms come closer. True or false? True. Okay. Correct answer. So if we see any material, even if it will have any defect, any opening or something, imagine it have this kind of opening, and we are applying any compressive force. So what will happen is this type of opening, it will come closer, and the chances of failure, it will be very low. However, if it is a tensile forces, this will become a weak point, and the what will say failure will be very sudden. So because of the repulsive forces of the material and other forces, when atoms are coming closer, there will be a very low chances of failure in terms of pure compression. So answer is correct, true. Next question is, during the excavation of a pile foundation, kaolinite and montmorillonite clay soils were encountered at two distinct locations. The locations where montmorillonite clay was encountered was excluded for construction as it is expensive in nature. Choose the latest defect type attributed to this properties of montmorillonite. Point defect, line defect, surface defect, volume defect. So we have taken this example before itself in different type of defects. Swelling of clay was one of the example of which type of defect. B, okay, line defect. D, volume defect. Okay, so answer is actually A, point defect. Correct. So if we uh, if we see from clay point of view, so in kaolinite we have one layer of alumina and one layer of silica. So this is a normal structure of kaolinite. So one after another layer are formed, and when water settle in between, if water settle in between, so it is type of inclusion, right? It is filling up the void in our clay layer. So why it is not volume defect is it's not in the three-dimensional area. That void is not a three-dimensional area. It is a layer by layer thing. So it is actually a two-dimensional thing. That's why we are telling the water will be filling in this area. Swelling of clay will be there. So that is a type of point defect. So difference between kaolinite is montmorillonite is kaolinite is like this AS, and montmorillonite is like three layer will be there, S A S. So that is a basic structure of montmorillonite, and water will be formed. Water will be filling up in between the layers of these, uh, in between interlayers of two different layers of clay. Okay, so it is a type of point defect. Is it okay? Or you have any doubt? Okay, so next question is, A and B are two samples of the same metallic material. Sample A was subjected to annealing and sample B was subjected to hardening. Using this information, which of the following is or are correct? A has smaller grain size and higher strength than B. A has larger grain size and shorter grain boundary than B. A has smaller grain size and longer grain boundary than B, or A has larger grain size and longer grain boundary than B. Anyone? Any guess? So first thing we will see the difference between what is an annealing and what is hardening. So whenever we are heating any material, and first we are heating it and then we are slowly cooling it, that is called as annealing. However, when we are heating it rapidly and uh, cooling it rapidly, that is called as hardening. Okay. So what will happen in the case of annealing is, we see the microstructure, it will be a, like we have a very big microstructures will be forming because of slow cooling. So there will be a easy chance for the material to cool down easily and form a bigger grain boundaries, we say. However, in hardening, what will happen, it will be suddenly hardened, suddenly cool down, so the grains formed will be very small. So that is uh, hardening. So now can you guess the answer? So if we see from this figure itself, A has a larger grain size, right? So A has a larger grain size and shorter grain boundary than B. However, grain size is larger, but grain boundaries will be shorter as compared to B. Here you can see grain boundary is very large. So answer will be B. Okay. Is it clear? Okay, then we'll go to the next question. Consider the following three statements. Silicon is brittle in nature in ambient temperature. Ionic bonds are prevalent in silicon. Covalent bonds are directional in nature. Which of the following is the most appropriate answer that best describe these statements? Both A and B are correct, but C is incorrect. A, B, and C are correct, and C is proper reasoning for A. B is incorrect, A and C are correct, and C is the proper reasoning of A. B is correct, A and C are incorrect. Any idea? So first option is silicon is brittle in nature in ambient temperature. So that is correct option only. We all know silicon is normally brittle in nature. However, ionic bonds are prevalent in silicon. That is a wrong answer. In silicon, we don't have ionic bonds. We normally have covalent bonds, and covalent bonds are directional in nature. So that is correct, right? So the answer is A and C are correct. A and C are correct. Any other way place we are telling, and B is incorrect. So option C is the correct answer. A and C are correct, and C is the proper reasoning for A. So silicon is brittle in nature at ambient temperature. How? Why? Because normal silicon will have covalent bond. Silicon covalent bond between different silicon atoms, and because of this directional bond, what will happen whenever we are heating it up and we are cooling it, the bonds will break because they are directional in nature. So that is why silicon is normally brittle in nature. Okay. Okay, so the next question is, figure shows the relation between the interatomic particle distance and lattice energy of two different materials, material A and material B. The coefficient of thermal expansion of material B is higher than of material A. True or false? So, what we were studying before is depending on the width of our well, we are telling about the coefficient of thermal expansion. So, if we see at any point the width of our well, so if we see at this point only, if at this point, if we see this point and this point, the coefficient the well width is more in case of A as compared to B. So the coefficient of thermal expansion of material A will be higher than that of material B. So the answer will be false. Okay. Okay, so next question is, what is necking? Anybody who have any idea about necking? Or in which type of material usually you will see necking? In ductile or brittle? Ductile, correct. So if we see in ductile materials, when in ductile material, whenever a tensile force is applied, let us take an example of mild steel. Ductile, and tensile force is applied. What will happen? There will be a the bond, the material, the atoms will start expanding, and show in the figure what will happen, material will start expanding, and there will be small inclusions or small voids created in the material. Those voids will expand, and this material will stretch itself. It will expand, and there is a at one point it will fracture. However, the this kind of cup and cone method, this type of failure is called as cup and cone failure. So at one point you will see a cup kind of thing, and another point it will be a cone. So in the normal inductile material only you will see this type of failure, and this figure which is formed, or which is this type of failure which is forming, it is called as the necking of the material. So you can see it's sort of our neck only, no? Very thin, thick, thin, thick, thicker part, thinner part, and thicker part. So that is called as the necking of materials. Okay. So this is the last question. What is annealing and hardening? I think we already discussed in the one of the previous question. So annealing is when we are heating the material and we are slowly cooling it down. And in hardening, what is happening? We are heating the material and rapidly cooling it down. So in case of annealing, what is happening is the large grains, they will break down, and the grain growth will happen upon slow cooling. However, in hardening, what is happening? There is a rapid cooling. Because of that, the grain growth will be very small, very less, and the smaller grains will be formed as compared to the in annealing. And other thing was grain boundary. So grain boundary in case of annealing is a smaller as compared to the grain boundary is compared to the hardening. So other thing, if we see from this diagram, this is mainly about the annealing processes. So what will happen is when we are annealing our material, we are the sorry the residual stresses is getting reduced, the hardness is reducing, however the ductility of our material will increases. So if we need a more ductile material, we usually go for annealing. However, if we need a material with which have a higher strength, then we will do a hardening procedure. So normally if we see our QST steel or TMT rebars, which you might have temper martensite, that are made with hardening. It is uh, heated and rapidly cooled down. So that's why we have a this kind of structure, which is softer from inside and hardened from outside because of the rapid cooling. However, if we are cooling it out slowly, then what will happen is complete material will be made of ferrite, or complete material will have a similar kind of composition because of the slow cooling. So that is what is annealing and hardening. So that's all for this week. If you guys have any doubt, you can ask me now, or you can put in the chat box. Okay, if there are no doubts, then we will close the class for today. Thank you for joining.